Okay, so this section is on refining transitions and optimizing collision energy. This is the next step after you have either generated your data-dependent discovery data or you've acquired information from the literature and you know which peptides you hope to target, or at least which proteins. So if we begin at the protein level, let's back up a second. So why refine? I think Brendan had this in his workflow too. The idea here is you don't generate any good quality data-dependent data from a triple quadrupole mass spectrometer. You do generate reasonably good quality data from an HRAM platform, but you still start off with data that was generated from a method that wasn't specifically targeting something. So you won't have lots of points across a chromatographic peak unless you're looking at the MS1 in HRAM, because the product ions you generate in data-dependent runs usually get 1 or 2 spectra. So you can't quantify off of that. When we want to try to quantify something, now we have to start thinking about generating enough points across our chromatographic peak so we can properly calculate a good peak area and its reproducible injection to injection. So we need to make sure all of the bits and pieces of these peptides we're monitoring are good for the instrument that we're using them on. So I'm going to go through some examples of working with a spectral library. If you're moving to a targeted method on a triple quad, spectral libraries data is usually generated on a different mass analyzer. So how do you know the charge state of your peptide is the same one you're going to see on the other instrument? How do you know the fragment ions are the same ones you're going to see on the other instrument? And so starting with the data you have and then refining it to make it work for your platform is the goal here. And optimizing transitions, not only picking the best ones, but making the method to generate them as reproducibly and as intensely as possible is going to provide the best quantitative results. Actually, I do want to stop for a second because there were some questions during the break. Does anyone have any questions about terms that I'm using? Because I've been doing this for so long, I take a lot for granted. Any confusion over acronyms or words I'm throwing out that just don't make sense to people? It's okay. Don't be scared. Okay, well, stop me if you need it. So, can everybody open up Skyline? We're going to generate a spectral library. You just need to open up an empty Skyline document. Yes?
Can you just tell me again the 3 folders that you wanted us to pull over?
Yeah. CE opt, transition selection, transition something, and library. Yeah. Okay. So does everybody have Skyline open to an empty document? It should look something like this.
Because you have Skyline daily, you might get a little update window that says, hey, update Skyline. Let's
skip it.
Now, just not because there's anything wrong with updating it, just because the Wi-Fi is a little slow, and all of us will be fighting for bandwidth to download it.
All right. Does anyone not have this window open? Because you don't want to fall behind on the first step, right? Okay. Okay. So the first thing you should do is go to, at the top, settings, peptide settings, and you should see this window open. Let me see. I'm going to do this along with you. Okay, so settings, peptide settings, and now you want to go to build the library tab and build a library. So library, build. So here I have, we try to do this like a baking show where we have the list of ingredients which are on your flash drives, right? And then I'm going to walk you through how to combine everything and make it work. And then we have the finished product, so you don't have to wait to get it all to happen if it takes a long time. And then also you have something to compare it to. So forgive me if I stumble through this and it's not streamlined because I don't do live demos very often with a large crowd. But here is where you're gonna build a library. You can name it anything you want. The finished product I have in there, I think is called NEU Skyline something. So I'm gonna just say test library 001, because it might take me 100 tries to make it work. Just kidding. So I don't do a lot of spectral library generation. By the time people come to me, they already know what targets they want, and I don't always need to have the spectral libraries there because I usually am given peptides to just start working with right away. So I am not the best resource for defining these actions, keep redundant library, cutoff score. This has a confidence interval that's based on your search results. It means it's gonna give you quote unquote good quality spectra. I don't know the best settings to have that on, so I go with default. Okay. And then this IRT standard peptide one, this is something that Lindsay will be going into later. So for right now, just hit next. Oh, that's because I didn't, sorry. You have to make a directory. Wait a minute. Hold on. So for the output path, you can probably go to your documents folder where you have all those files put and make a library folder. New folder. And then put it there. And so it just needed that output path front part. And so what it does is it takes the name for your test library that you put in there and it tacks it on the end. So you need to have the output path. So that should be pretty straightforward. Is everybody with me so far? Okay. Next. Yes. So this part is also kind of easy. Here, the input files are going to be your searched files from your data dependent runs. So I've generated some for you. If you go to add files, and see, I didn't move my thing to the documents, shoot. If you go to that directory, that should be library generation. Nope, not that one, sorry. Uh-oh. It's not in here. Okay. So let's pretend for a moment that there's a directory filled with MSF files. I will walk you through how I would do this. Let me go add files. And so normally what you would do is you would find your directory where your searched data files are. And Skyline fortunately looks for specific file extensions, so it can help you find them quickly. Sorry, this should have been searched HRAM. I can give these to people and I know that they're online because that's how I gave them to Brendan. And I'm sorry, they just weren't incorporated onto your USB drives. So what you would do is so these files are recognized by Skyline as inputs for generating spectral libraries. So I would select them all. Questions? No? Okay. And then finish. And so you can see down at the bottom, Skyline is working on chugging through the list, working on generating a spectral library. And if you want to make sure that it's in use when you use Skyline, I just check that box. And I hit OK. Okay, so I'll make the library, so the searched data files, the .msf files, that's what right now you don't have access to, but there should be a spectral library file on that flash drive. So let's just look, because that's what I'm working on. So, oh, we made them. So we generated data and searched them in a search engine. The .msf comes from Proteome Discoverer. Okay, so the spectral library that I am now generating, you actually already have. It's made. It's the baked cake with the icing on top. So if you go into the library generation folder that you copied over and you see the file name right there, just click it so you can copy the file name. And then I'm going to open a new one, settings, peptide settings. So in your library generation, you can go to edit list, add. Everybody with me so far?
Oh, sorry.
Who's having problems? Raise your hand. Okay, where's your problem?
Can you go back to where you showed that?
Sure.
the change requirement?
It's under your library. It's the only file under the library generation directory from the flash drive that should hopefully be in your documents folder now. So don't double click on this. You just want to get the file name so you don't have to type the whole thing. So just right, just so this is the file that you're going to be looking for from within Skyline, okay? So when you go into that Skyline, you go to path, you find where that is, that library generation directory is on your documents drive now. Sorry, for me it's on, for me it's in a different place, but you click that file, the blib. Everybody following along? Fair enough? Okay. So for me, I don't know if this is something that I'm just doing incorrectly, but Skyline doesn't copy the name into the name part. It doesn't automatically update it. So I'm gonna put the name of my library. I'm just copying and pasting the name. I'm removing the blib extension because I think it might add another one to it, but you should have something like this. This initial file, this path will be different for yours, but you wanted to have a directory to where that blib file exists in your documents folder, and you want to have the name of your library. Yes?
Just so when we get our raw data and we're going to put in, does it like represent the biological reference together, technical reference
No.
in this library?
No, this is data that was kind of generated for this.
Oh.
Yeah.
Okay.
No, it's a fractionated plasma sample. So it's like 48 fractions of plasma that was done offline, and each of those 48 fractions was injected onto a Q-exactive using nano, maybe high flow. That part doesn't matter, and then it was searched against a human proteome database. Okay. Now we hit OK. For me, it already exists. I'm going to hit cancel and just check it. Okay. Did that work when you hit next? No. Okay. What kind of problem is this?
Anybody else?
So,
See you guys helping each other. Excellent. All it takes is one person and then it can spread.
all the way out there.
Confusingly intuitive. Once you figure it out, it's like a lot of stuff.
Oh, yeah. So here, edit. problem. Oh, good. That's helpful. Okay. When your library file is made, make sure it's checked so that it will be used. Okay. And then you go. Okay.
Librarian filter or filter?
Don't worry about that now.
Okay.
Yeah. For now, just make it be there. Okay. And so this file, this slide right here, it's kind of meant to walk you through in order what you would do. You would open up that library tab. You would click, when you have access to those MSF files and you can actually build a library, you would click build, build library. You would populate this with where the file exists, the file name, hit next. You would select those MSF files. These are the exact ones you're gonna get. I'm sorry that you don't have access to them right now. And then you would click add files. And then under peptide settings, you should see this, or sorry, peptide settings library. You would click the box and it should be there. Now, or at least it'll start building. So that didn't go as smooth as I thought, I'm sorry. But back to the presentation. So now you have an empty Skyline document that has an invisible library that you can't see, right? So that felt like we just did something useful, didn't it? It'll come in handy in a little bit. So how do you pick your peptide targets, right? So we have empirical data now in your spectral library showing which peptides have been detected by a mass spectrometer. Now, if someone came to you with a list of peptides and said, these are the ones I want you to detect, you could put them in Skyline and see if they're in your spectral library database, and that would be great. If you just are curious as to what peptides are in there, you could import an entire human proteome FASTA file, which is all of the proteins that are present in the human proteome whose sequences are known, and then Skyline would automatically tell you which ones are in there in your spectral libraries. And so this gives you a couple of options. So this is option A, where you import does everyone know what a FASTA is when I'm talking about this? This is the form that the proteome databases are in. That's just a file extension. So you can import a FASTA into Skyline, and you could have it follow like a filter to pick peptides for you that match the spectral library database. Or if you have a set of peptides that you already know what you want to target, you can insert the list of peptides and transitions into Skyline. And then once they're in there, that's when you can go through the refine and optimization process. So this goes back to the earlier example. You'll notice that I have some slides that are repeated occasionally throughout the 2.5 days. That's number one, to make sure you catch them if you fell asleep the first time. And two, because I just find them to be really important. So someone had questions before, like, okay, so this peptide, oh, let me walk you through too. This is from, I picked plasma peptides that I had on a list. And this was, I was doing some stupid, that was recorded. I was doing some things for Thermo. They aren't stupid at all. But we wanted to showcase our instrument performance. And so we had these plasma spectral libraries from a Q Exactive, and I wanted to see when you detect them on a Q Exactive and they're fractionated. If I take the neat sample, which is unfractionated plasma, and I look at it on a triple quad, can you detect it? And so the point being, when they're fractionated, they're more concentrated and you have a higher chance of detecting them in a fractionated sample. But then when you take that whole plasma sample and put it on a triple, can you see it? So that was the goal of this experiment. And so I had to figure out which peptides to target. So I took all the peptides that were identified, the entire list, which was way too many to do on a triple quad all at once, or at least with the time I wanted to spend. And I sorted them according to intensity, and I picked like every 10th peptide, so I had the entire range of intensities that were identified in my spectral library. And then I took those peptides with their protein names, and I imported them. And I'll show you how to do that in a little bit. And then anything that has a spectral library associated with it has this little stick figure thing next to it. And Brendan can explain better what all these little icons are, but like one is a protein, another is a peptide, and that's a peak. So if you look closely, it's kind of intuitive. And then here, what you see in these spectral libraries, so first, when you click on a peptide, it'll show you the spectral library that's present with the particular precursor that you're on. So with this one, it's a 2+, which is that one. And this is a manufactured screenshot thing, so I added in the +3. Normally you wouldn't be able to see them one on top of the other like this. So this is for illustrative purposes. And if you click on the +3 down here, you would see this one. And then as you click through each of these, the fragment ions that they are will turn red. And so you can see which one gives you the best signal. Obviously a rank 1 would give you most intense signal, and so on. And so you can set up Skyline when you bring in a list of peptides to say, because Skyline doesn't, it's going to do what you tell it. So if you give it a peptide and you just say, I want to see product ions, it's going to say, well, I can give you them all. Or if you give me some rules, I can follow the rules and give you ones that you want. So we usually pick ones that say the fragment ions must be present in the spectral libraries, so we should see data from those. You could pick additional ones if you need to, and explore data that way, but point being is, if it has a rank here, it's shown in the spectral library, and you can go through and sort of look at the quality of the data to figure out, should I pick the +3? Should I pick the +2? And then when I pick those, which product ions should I pick? So, can anybody, you know why we tend to look at the high master charge range for product ions and we tend to ignore this lower range? Does anyone know why that is? It's kind of by convention these days. Right, selectivity. So that was a test to see if you were awake. Good job. Earlier, what I had said was Y3 and Y2 ions tend to be really abundant, B3 in this case, and that's nice. That gives you intensity, but that doesn't give you the selectivity of making sure that that B3 or Y3 ion is from this peptide. And so, for example, a Y3 ion here is 1, 2, 3. It's FLR. If you did a database search and you looked at how many peptides ended in FLR, there would probably be a lot. They may not chromatographically collude with that one and it may not interfere, but why risk it if you have all those other ions to choose from? Now in some cases there are peptides that are really short, and so a Y3 ion is something you are stuck with, and that's okay. Yes?
I have a question. You have, let's say, 10,000 peptides, so many Crohn's or inflammation cells, but then is there any way I can pick those which are good easily rather than go one by one?
So you can, once you have data that's measured in a targeted way in Skyline, so that's the easiest way. If you take your list and you just try to target everything, you may have to split up the list into several different methods, and you inject the sample and target a subset of a big list and keep injecting the sample until you finally cover all of your transitions that are represented. Then what Skyline will do is it'll take in the data and it'll show you the peaks from each of those peptides on the list, and then you can sort the peptides by intensity, and so you can see your tallest, your smallest, everything in between. And if you decide that there's a threshold that you don't want to pay attention to, you can just get rid of those. Personally, I go through it because at the end of the day, I am not the person making any kind of decision from my data. It's going on to someone else to make a decision, and I want it to represent the best quality data that there is, or that there are. And so I go through it manually. There are tools like that sorting that make it easier. And there may be people that have confidence in other ways to do it in a more streamlined, let the software take care of it approach. But I have not done that. Yes?
What if your modification is on lower and so is picking the higher sufficient to say that
Right, so the question is, if you have a modification on your peptide and if the fragment containing the modification is down here, but you're concentrating on picking fragment ions up here, are you worried you might miss evidence that the modification is there? So, okay, the good thing is a modification on a peptide adds mass, and that's reflected in the precursor. So you'll always see it here. And then any fragment ion that contains that modification will have that added mass to it. So for isotopically labeled things, that's great because they stay in the amino acid. They're not technically like a side chain, an additional modification. When you're talking about post-translationally modified peptides and adding groups like phosphos or I don't know what the other ones like glyco groups or things that can be fragmented off, that is a more challenging thing to be concerned about, especially on triple quads, because sometimes modifications, when you take the peptide and you isolate the precursor and you fragment it, sometimes that modification is lost and you get the bare peptide mass and you don't get any fragment ions from it. That's what's called a neutral loss, and that's common in phosphorylated peptides. So if you need sequence information, then you need to fragment that peptide, and there are tricks on how to do that. If you need site-specific information about that modification, then that's another, like, all right, now you've got to concentrate on that experiment, and working with samples that have an abundant amount of that target present is good, because then you can do some optimization, or ideally, if you can afford a standard, then you would just kind of want to play around with that. But as always, when picking transitions, having a spectral library is nice, but unless it's the exact same sample in the same form that you're going to target your peptides in, I like to take my samples and look at them in sample background to see what kind of interferences may be potentially causing issues with these. Because again, you might pick like, oh, this Y7 is great, it's the most intense. But then when you go to analyze your sample, you might find that something completely coelutes and has the same mass to charge and product ion as that. And then that's a useless transition for you. So starting here is a starting point, which is why it's the refining process. Yeah, so that's kind of what I was getting at. So this is data from a Q Exactive, and I don't trust any of this, to be honest. Use it as a guide, but I don't trust any of it until I generate my own data on the triple quad. And then I begin to make sure, like, oh, that does look like a peptide. All the transitions are eluting, and I'll show you that in a second. Oh, so that's the labeling. If you right-click in these spectra, there are properties of how things can be laid out, and you can label B ion. You can have the B ions labeled. I don't know if that's the default setting, but if you enable it, the B's are one color. They're, I guess, the purpley. Y's are blue. You can also label C and Z ions. Those are ions you wouldn't normally see unless you're doing electron capture dissociation or electron transfer dissociation. And A and X ions are not normally observed, but you can label them if they're in there. And then the precursor is green because that is what they call unreacted precursor, which means you didn't fully fragment it, so you could generate more intense ions if you adjusted the collision energy. And so seeing it labeled there is helpful because you're like, oh, I can optimize that. Okay. What is the dot product? This is something that is really helpful when you're going in to look at your spectral library and then you're looking at triple quad data to see, is this the right peak? Because you don't always get a beautiful peak in your chromatography. Sometimes you get a choice of a dozen. Sometimes you get a signal that's so low it's in the grass, and it's really hard to know if you're picking the right peak. And so dot product is a way to correlate the contribution of each of all of the product ions that's observed in the spectral library, so mass to charge and intensity, with what's observed in your actual data. And perfect is 1, and you'll see dot product with a score range between 0 and 1. And so This is a paper that just goes into the specifics of what dot product is, because that's the best I can explain it right now. I'm just like, oh, I want a dot product of 1, so that's what I look for. But this goes into details. It's like a vector system, and it's very good at correlating HRAM spectral library data with triple quad data. Yes?
So earlier you showed a slide how the molecular numbers of the product ions are dependent on the concentration of the peptide. So where the perfect is 1, will those scores go down with the less concentration of peptide you have between samples?
That is a great question. So as long as your peptide is within the linear range of detection, which means it's above your lower limit of quantitation, the dot product should match, right? When you're below the limit of quantitation, so what that means is, what it's getting at is when you fragment a peptide, because of the way the physics work, the peptide will fragment into the same product ions under the same conditions and generate product ions with whatever intensity they come out at, the same way all the time on every version of that instrument. I've done this experiment where I've generated product ion spectra like this on like 5 different linear ion traps back when LCQs were like the big thing. And the reproducibility of their ratio in a single spectrum, the biggest is always the biggest, the smallest is always the smallest, and then whatever's in between is in between, that is like within 5%, even on different instruments, because that dissociation process is so reproducible. So that's why dot product works, is the data are broken down into mass to charge with an intensity value, and then it just compares that to what you get on another instrument. And as long as you're within the linear range of detection, it should match and it should be great. If you're below that, then those ratios do not work so well. And I have more details about that if anyone's confused. But here is pretty much how the dot product works. So when I import my triple quad data, like let's just say I made a rudimentary list with a lot of potential product ions. This one has 1, 2, 3, 4 for this peptide, the FLEQ. This is the chromatogram that was imported, and Skyline's picking this guy at 45.2 minutes. And I'm like, why would you pick that? There's this big peak right here, and this other big peak. But if you zoom in on these, the one at 35.1 minutes, which is the first one, it has one very large intensity, and the others are really, really small. But the dot product's 0.37. The really big one at 50.9 is enormous, and it has really big one and a second transition, but not anything from the other two. And its dot product is 0.16. So I would definitely not want to use that one. And then the one that Skyline actually picked, Brandon would be so proud. It's very small. The intensity is very low compared to the others, but when you zoom in, all 4 transitions perfectly collude. They may not look that great, but they're all under the same general peak area, and there's signal for each and every one of them. And we saw that in the Spectral Library. That's why we pick these transitions. So that's a very good confirming bit of evidence. And the dot product is 0.92. So we have high confidence that all of those product ions are coming from that peptide, and that's the peak that represents the peptide eluting. I see looks of concern. Are there questions? No one's concerned. Okay, that's good. I will also say, you have these Skyline files. So this is a data set. I forget which directory it's in, but you can open up the Skyline file, and these data are in there. So during a break, or if we have time, whenever, we can walk through. So this is the peptide name. If you do Control F in Skyline, you can search in FLEQ, and it'll, it's just like Excel and those other programs. It'll find that peptide, and then you can see some of these examples live. Okay. So retention time is another way that we can make sure that we're picking the right peak. Now, Lindsay will go into retention time this afternoon, but the idea here is that the peptides are made up of amino acids. Amino acids have a certain hydrophobicity, which means will they elute early or late in your gradient, right? And that can be calculated, again, a little bit rudimentarily, but it gives you an idea of things with a low hydrophobicity score will come out earlier, and things with a higher hydrophobicity score will come out at a later retention time. And then you can draw a regression in all those data points. And you tend to see something that kind of looks like a line. It doesn't look like a great line when you first import data into Skyline, because Skyline does a great job of picking peaks, but it's not perfect. And so things that are on the periphery here, you can go in and just double check to make sure that Skyline picked the right thing. Why is retention time important? Because eventually, if you have a method that you want to use every single time, you should know where your peptide comes out, and it should come out at the same point every time. And you can even set up your method to target just for those peptides just when they elute, so you're not wasting mass spectrometry time. And so making sure that you have a good regression, and in my experience, most peptides really adhere pretty decently to this regression. But there are ways called indexed retention time where you can make it a little bit more refined. But the point being here, if you right click in the retention time plot, and you look at linear regression, each one of these dots represents a peptide, and the one that's red is the one that you have selected. So for right now, actually, let's open up that data set. Let me tell you which one it is, because I think that'll be helpful. Nope. I really hope I put it there. Nope. Yes. Under transition selection. If you open up, you can either double click the little icon that doesn't have the red squiggle on it, or you can go into Skyline and point to the example carboxymethyl N versus Z, blah, blah. Somebody let me know when it opens so I know that it works. Okay. All right. Oh, crud. Okay. Does everyone have it open? Enough? If you Control FLEQ, you should be able to find this peptide I'm talking about. Is everybody here? Good enough? Okay. So some little ways to navigate in Skyline that I find to be very helpful. So first, if you hit right now, Skyline is set up to zoom in on these peaks because they've been picked, and it wants you to see them nice and clearly. But I want to see the entire gradient. I want to see the entire chromatogram. So if you hit Shift F11, you should get that. It should zoom out. And if you look at over here on the right, you can see the report on the dot products of all the peaks that are being shown. And so you can look and see if there's a better option than what Skyline picked by default. Okay? And so this is kind of like data without human intervention at this point. Okay, so that's a file that you can, if you want to walk through these slides or if you have questions about them later, that's the one that gives a good example. But back to the FLEQ peptide. So what I had mentioned about the retention time, on the lower right-hand side, there's that retention times plot. If you right-click and go to graph, linear regression.
Sorry, how can you open this window? It's not open with the retention.
Oh, go to view. We'll go there first, sorry. View, and then retention times. And then go to, we're going to want linear regression. And then, oh yeah, that's a new feature, sorry. Score to run. And so score to run, obviously there has to be something that it plots retention time against. This is a hydrophobicity calculator. It's based on the amino acid sequence. it doesn't take post-translational modifications into account. So if you have a peptide that's modified, it's going to predict the same retention time, or the same hydrophobicity. Okay, and all of these screens, all these windows, you can click and drag them if you want to see them bigger. It's kind of a nice feature. And then they're also interactive. So if you click on a peptide, or on a spot there, it'll bring you to that peptide. So if you want to see which outliers, which these guys are, you click on them, and then you can redock this back down and figure out, like, oh, which peak is the right one? That could be why it's an outlier, because there are a lot of seemingly good options for that one. Okay. So for this FLEQ peptide, this is the peak that Skyline picked, and that's the one that has a really nice dot product. And what's nice about it is it's really close to our regression from the data, and the other two are not so good. So not only does it have a lower dot product, but it's a little bit higher than the line, which is not that different from a bunch of other peaks, but it's not as good as this one with a nice dot product. So it's just, again, like more evidence being like, oh, if it looks like a duck and it quacks like a duck, then, and this one is far away. Now, there are cases where you're going to see things that don't jive so nicely, and the dot product might be low, but it adheres to the retention timeline, or vice versa. And that's just because nothing's perfect, unfortunately. So here's a more difficult example now. It's still in the same data set that you have, and I have the peptide down here, VPLQ, so you can control F and find that. So if you zoom out, this is the spectrum, or the chromatogram that you should see, and there are a bunch of options. They're all kind of jumbled up in here. So dot product of 0.71, 0.56. Oh, I took off the indicator of what Skyline picked on here, but Skyline probably hasn't picked on yours. So don't use that as a cheat. And if you didn't have that on there, the question would be like, oh, which one should it pick? I would probably initially look for like the biggest dot product. So I got a 0.77 there, or 0.73, 0.74. They're all about there. But I probably wouldn't pick the biggest one, right? Because that's 0.56. And so the real peak is not even this one. I think it's this guy. Yeah. It's this jumbled up little bit of crud. Sorry, I shouldn't say that. And it doesn't even look that much like a peak, because if you zoom in, this is what you see. But the thing that you get here is that every single transition lifts off from the baseline. And the way that visually, the way that I look when I go through and I screen these for peptides, I look for just that little white bit and nothing on the baseline. If you ever have a complete flat signal for a transition that you observed in a spectral library, it's something that you're going to be like, I don't know that I feel comfortable with that. There should always be a little bit of something, unless you're monitoring like all 20 transitions or something. But I always kind of, my eye jumps to that now. I look for that same repetitive thing when I look for all my peptides. And then you can see it's decently close to the curve, retention time-wise. If I picked anything at 50 minutes, it would be up in this region. It would be just an outlier. Okay, so this is the last difficult example we have with a spectral library. So the peptide shown there, you can jump ahead to it. And the question is it this one? Or is it the 0.88 dot product? Or the 0.68? I don't know. I know they jump around a little bit if you zoom in and zoom out. They don't always show. And Brendan would be the one to answer that.
I had a couple questions from students. So not all of the peptides in this target list are going to be able to have a dot product, because you have to have a spectra in your spectral library
Yes.
for that peptide to calculate dot product at all. So you got to check. Sue had mentioned the little icons next to the peptide sequences in the target list. So next to that, if there's not that like 3 big lines, so like really reduce
These little guys.
the representation of a spectra. So you click on those, you should be able to see the dot product and the dot product listed next to it. And if you want to look at the spectral library for that, I think it's under view. You can look at spectral match. You can bring up that window. You can see the library
So when given the choice between the big tall one and the bottom one, I mean, obviously dot product is showing us that it's kind of leading the way here. However, this small one, even though it's got a great dot product, if you pick this peak and it applies that retention time to the plot, it's up off the line. It's more of like an outlier. But if you pick the big one with the smaller dot product, it's closer to the line. However, I don't like this one because that blue signal is right at the baseline. There's nothing. It's a flat transition. And that's just, I rarely see peptides coming from spectral libraries, or when I start a transition list, I rarely see, especially when I'm only targeting a few, I rarely see a total flat signal there. So again, this is why I look for something where there's no signal at the baseline. You just see that little thin baseline line from plotting. And over here, you don't see that. So I would have less confidence in this. And obviously the dot product would agree with me there. But the retention time may not be perfectly adhering to what we would hope. Yes?
Can you reorient me really quick? What we're looking at is actual raw data that we generate. Okay? And then it's compared in with this
Spectral library.
Spectral library. Okay?
Well, not a theoretical spectral, it's an actual spectral library generated. So the spectral library was generated from high-res accurate mass data, searched against a database, and then you can see if you go into there's a view in Skyline, you can see the spectra. It's like the view MS, I forget what it's called. And then
For all of the peptides that would be in there.
yep. And then a method was generated based loosely on that to make triple quad data and to target all of the transitions that are shown, plus others, and then plot it. And so this is showing how well the spectral library agrees with this data, and then this data plotting it to make sure that our retention time makes sense with like where the peptide's eluting and picking it properly and stuff. And so actually here's a good example too. I mentioned that this SSR calc is a hydrophobicity predictor. This 100 angstrom is based on the pore size of the columns you would use, and so you can also put in 300 angstroms. Those are two of the provided settings. But the problem with it is that if whatever your peptide sequence is, it's going to calculate a value. It does not take into account modifications. This has a carboxymethylcysteine, so it was alkylated with iodoacetic acid. And so that made a modification to this cysteine, which kind of messes up the prediction, which is probably one of the reasons why it's not adhering close to the retention timeline. And so these are things that, like, when you're looking at data and you think it through, it makes sense. But quickly taking a snap judgment of biggest peak, closest to line, no, it doesn't always work that way. And so going back to the question, like, is there a way to have the software just kind of do everything and generate the list? Like, yes, but. And so it's kind of hard. I would love for it to be faster and more streamlined, but I'd be out of a job. So here are cases. In this example data file, this was something that we had done where a customer came to us and said, and everything's been anonymized, I hope, but they didn't buy an instrument anyway, and we're not trying to do anything with their data other than illustrate to you. They had a list of proteins. They said, we want to detect these proteins on a triple quad. And so a colleague of mine generated the spectral libraries in normal and cancer. That's what the N versus C is. The normal plasma was his own. He's crazy. He draws his own and like preps it. And then we set up a targeted list. We didn't know what peptides to target because the customer just said, I have these 6 proteins. We're like, okay. So we based as much as we could off of the spectral libraries, but there were proteins that they had on the list that generated no spectral data. So you're like, oh, what do you do? So here's an example where this peptide doesn't have a library associated with it, so we don't get dot product. And there are a lot of nice peaks here, but thinking about something I said earlier, and I may have mentioned more than once, which peak do you think it is? Who said it? Yeah. Why? You see how that kind of jumps out at you? So this is one of those things where, like, I don't know, it's like, it took me a while to sort of make that work. Now every time I see it, my heart feels happy. Now this one, it could have been, maybe, because everything is lifting off a little bit, but not as good as that 37.9. Oh, yeah. So we weren't right. So here we are looking at the data zoomed out, and the 37.9 actually looks pretty decent. But when you zoom in, what do you notice about it? There's like, that purple one might not actually be part of this one, so it could be an interference, or it could be a mixture of things, and that's where it is on the retention timeline. All right, well, and then the one at 43.6, this again, you can see that not it doesn't have the same apex. They don't all line up, but they're just kind of shifting all over the place. And so maybe, and it's not so close to the retention timeline. So this one, 45.6. Why would I like this one? I mean, it doesn't look that great. I don't know. Would you like it? So one way that we can figure out if we like it or not, right, is we generate more data. So we had normal and cancer samples. And the goal, obviously, is to find some kind of response difference between the two. Whether it's up or down, we didn't know. So here is the normal, and here's the cancer for that peptide that had the green check next to it on the previous slide. And so we went through, and in the case that you don't have, you're not sure, I don't want to say that you can pick several peptides at different retention times, because you really can't in Skyline. But what you can do is target for the span of time over which all of those peptides are eluting, and see which one gives you this kind of response. And so in all of these cases, these are the normal, those are the cancer, those are the normal, those are the cancer. And that confidence led us to believe that that was probably the right peptide. Then we looked at other peptides from the same protein, and they had a very similar fold change between the two samples. So that gave us even more confidence. Is it the right peptide? I honestly have no idea, because we don't have standards to like verify that. But as a starting point, this is, again, just giving more confidence to our data.
Isn't that an assumption that it's going to be different from normal?
It is. Well, it was, we weren't told anything, but then when we went back, they're like, yeah, that should be more. I mean, that's the whole point, right? You don't want to detect something that's disappearing to have it be diagnostic, because not detecting something doesn't mean it's not there. It just means you can't detect it. And so ideally you would like something that's increasing to show presence of a disease or a condition or whatever. And then we lucked out with that one. So. Okay, more tips and tricks. So duplicate transitions, this has a lot of different ways to explain it, or the terms. But, well, peptides first. So when you take your spectral library and then you decide to target a list of peptides, I don't know why I always tend to mess this up, but for some reason, when I take a spectral library database and I make it in Skyline, and then I add a list of peptides, I always have 2 of the same peptide just somewhere on my list. And I have hundreds of peptides, and I can't scroll through each one and like delete. So there's options in Skyline where if you have a list and you go under Edit, Refine, there's Remove Repeated Peptides and Remove Duplicate Peptides. Remove repeated peptides means if there's more than one of that peptide in existence in your list, it kicks out both. And remove duplicate peptides gets rid of one and gets rid of all and leaves one behind. That makes sense? So it's a tricky thing, but if depending on the quality of data that was generated in the spectral library, the list that you have, how it was generated, who gave it to you, how well you trust them. This is always an important thing to do, because if you have the same peptide coming from different proteins on your list, how do you know which protein that peptide came from? There's no way. So one is, why monitor for it at all? Kick it out. Or if it is very important to a particular family of proteins and you're monitoring other peptides from that family, you may want to keep on a version of it. But this is just one way to help refine your list and decrease the number of targets. Okay, so going back to fragmentation, and relative ion ratios. This is what I was trying to describe for the dot product part. When you fragment a peptide, this is an example of this one up here, you get these ions, and their intensities should be relative to one another, the Y8 to the Y4, the Y8 to the Y5, the Y8 to the Y6. That should really be consistent every time you monitor them, as long as they're above the limit of quantitation. And this was a lesson I learned hard in grad school, where I was monitoring a peptide, and I was looking at 2 different cell lines. One was drug resistant, one was drug sensitive, and I was looking at these ratios, and I noticed that when I took the Y6, I just chose one at random. I chose the smallest one, I guess, and I normalized the intensity of the others to the Y6, so everything's a bigger number. The Y6 was 1. If you normalize the Y4 to the Y6, you get 2.1. Y8 to Y6, you get 3.85. This is what I determined for my standards. Or these are the light, and those are my heavy peptides. This was data generated from light peptides and heavy peptides with no sample background, so no chance for interferences. And then when I looked in my sample, the light version of this peptide, the ratios are all way off. They don't agree at all. But the heavy agree reasonably well with what my heavy was with no background. And so what that led me to believe was that something was going on in my light peptide signal, and it was causing an interference. And this was the way I was able to justify not using that peptide, because I could explain it. But this is something we call a relative ratio or a product ion ratio, where you look at the fragment ion patterns. So it's not just mass to charge, but their intensities relative to one another. And this is just another level of identifying your peptide and making sure it's the right one and making sure it's not interfered with. Okay. And again, this is a repeat yet important plot visually. Instead of looking at a table of numbers like that, visually you can look at that and be like, oh my gosh, it's totally different, right? Jumps out at you. Okay. So other things that you can look for in your data that may not be necessarily looking at chromatograms or fragment ions, but when you plot your data, like I mentioned earlier, you should see a response. That's every time you add or increase the concentration, your signal should go up. That's just kind of how it works. And if you're able to plot the data on a log scale for your concentration curves, it separates those points out so that you can see them visually. And so this is from a paper from 2009. This was my first work in Steve Carr's lab. And it's showing 6 different peptides and their responses. Now what we should see is each color is a different transition for this one peptide. And we should see the response of all the transitions going up all at the same time. But this one is like flattening out at the low concentration level. That's because there's an interference here. So that peptide is the same one as this, where it had this huge interference in it, and then it doesn't really seem to be much of an interference at high spike levels. And so on a plot, it would look like this. That's that purple transition. Okay. Here's another example of an interference. Interferences tend to be easily recognizable because it's one transition that just peels away from the others. Because in a response curve, all the transitions should track together. But when you see like that, or like this, one transition peeling away, then you know it's probably an interference from something else. Here, you see all 3 transitions flattening out. I know the word is up there, but does anyone know what causes that? If you're running a calibration curve in a complex sample, that's the other end. That's the next one. But this is actually because you're able to detect that analyte in your sample without spiking it in. So that's called endogenous. You're detecting endogenous levels of your targets. So CRP is present in plasma at reasonably high abundances. And so when we were spiking into it in our blank, we saw it in our blank too, but at the low level spike, it wasn't reading as a low level. And that's how we tell, because all 3 transitions track together, so you know it's the analyte. So saturation, that's this one, where a couple of the transitions are plateauing, but one of them isn't. Does anyone know why that is? Does anyone know what saturation is? Does anyone not know what saturation is? All right, saturation is when the amount of analyte going to your detector is so high, your detector's tapped out. It can't register anymore, so it reaches its max and it's like, I'm done, and it gives you a flat line. So the reason that the signal is plateauing for these two, but not this one, is because that's the weakest intensity transition, and there's still room for it to generate more signal from the detector. Yes?
Hi, I have a question. What instrument was it detected on? And would we see oversaturation on all kinds of instruments?
Oh, this was a Q-trap. Yep. So saturation can be detected on a triple quad because ions are they're being collected in a beam-like fashion. On other instruments like Orbitraps and FTICRs, because you're not detecting signals hitting a detector or a multiphoton or some kind of detector assembly, you're actually monitoring their image current. And there are other things that instrument vendors have in place called AGC, automatic gain control, which prevents you from overfilling or saturating and causing that kind of effect. So this is more common on triples. That's a really good question. You're testing me. So this is one where there's just, it's all over the place. There's no correlation. It was not detected. This, by the way, this black line is the theoretical, what we would expect the response to be. And so this was not detected, which if you saw the data, you would understand. This is the peptide from myelin basic protein. This was the N-terminal peptide that got chewed up by exoproteases, and so it should have been there. It was there when we spiked the peptides in, but when we spiked the protein in, we didn't detect it. And then this one, you would maybe say, oh, it's not detected, but there is a kind of correlation with this. And if you looked at the chromatograms, you would see that the electrospray was very unstable. And what gave rise to this wasn't that it was really jittery, it was that the peak came out in about, in a very narrow window, so we only got 4 points across the peak. And so it wasn't able to correctly, appropriately, reproducibly get good peak areas every single time. And so that's the response that you would see in a plot. So I tend to be really visual, and I like to see things laid out easily. And so this is why I like people like Brendan and D. Armani, because they make plots like this for me. So how can you see these things? Tomorrow, D. Armani, he is a doctor, but his initials are ER, so it's confusing, but anyway, we call him Mani. He listens to me when I was talking to him about that interference thing and looking at relative ion ratios of product ions, and then also generating curves, because we would give him data, we would export things out of Skyline and CSV files and these big tables and give them to him, and then he would give us PDF files with these nice plots back. But there was always that like back and forth. I'm like, no, I just want to press a button. And then I also want to see, can you predict interferences? So I worked with him to get data and to test things to generate this thing called audit, which looks for inaccurate and imprecise and interfered with transitions. And then in the process, he lumped in LOD, LOQ calculation, and then generating these response curve plots when you have that kind of data. And we called it something called Quasar. It's the external tool that's available in Skyline. And what's nice about it is this is before Skyline had calibration curve support. When you would plot this, these little tick marks at the bottom are notifying you that something's up with that transition. Either the reproducibility is bad, or it could be an interference. And so for these, it was just the reproducibility wasn't so good, so they're all kind of marked off. And it does it at a transition level, not at a peptide level, so you can keep the peptide and make sure that you either remove a transition or change it. Okay. So auto interference is something that people don't think about. A peptide interfering with itself. You kind of think like a palindrome word like radar. It's like spelled the same forward as it's the same backwards. It's kind of the same way with peptides. Not that their sequence is a palindrome, but when you generate fragment ions from a peptide, sometimes a Y ion and a B ion will have the same mass to charge. And because they're coming from the same thing, then they will both give you signal at that mass to charge, which is not usually a problem if you're identifying a peptide. But if you're comparing it to a heavy form, well, that heavy form now doesn't have that same BY interference issue, because usually the Y product ion will be heavier. So you need to make sure that this isn't happening to you. And why is it important to pay attention to? Because if you look here, we've got a Y6 and a B7 that have the same mass to charge. This is nominal mass on a triple quad, so you wouldn't be able to tell these apart. They'd be one peak. And a lot of people would be like, oh, my IQ exact take care of that. Nope, it can't, because you would need a resolving power of over 600,000 to separate out these two product ions. So the way that you determine the resolving power required is you take the delta mass, these are rounded, but you take the difference in mass between these two ions and you divide it into the average mass of those two ions, and you multiply by a million, and then you get that. No, you don't have to multiply by anything, sorry, scratch that. But if you do this process, then that is the resolving power that would be required, and that would take like over a second every time it would generate a scan like that. And so the best thing is just to avoid that transition and not use it at all. So the next few slides go through how you can test for auto interferences or self-interference. And this is just another example where you see, and this is where the color coding of the B ions and the Y ions, it's nice to see them because you can actually see, oh yeah, there is one there. There is one there, but what if you don't have a spectral library and, you know, or the contribution's so low, like how do you know how much interference you're probably going to get? So you can do an experiment for this. If you have light and heavy forms of the peptides and you just combine them at 3 different ratios, run the experiment, and when they're 1-to-1, you should monitor a bunch of transitions, at least 3 if not more. Most of your transitions should have that same ratio, but there are going to be 2 that might not. And that is going to show you the interference potential of the light and the heavy causing the same product ion being monitored to have inaccurate results. Does everyone understand that? It's a little tricky. And this is one of those like nitty-gritty things about peptide quantitation.
So you said that this would happen when there is the B and Y ion being generated which have the exact same mass, right? So even if we were trying to quantify it, because in the previous slide you said that the ratio would remain the same, would it make a difference in the actual quantification of what we're trying to measure?
Yeah, and that's what this shows. So here we mix our light and heavy known ratios 1-to-1, 1-to-20, and 20-to-1. So these should be the calculated peak area ratios for each transition, and you can see the differences. So the Y10 and 11 are fine; they're not interfered with because they're 1, 0.05, and 20. But the Y7 and Y8, which is each of these has potential interference from the light peptide form. That's when you see the product ion ratios change. So they should all be 0.05. But this one's got a 10% interference, reducing its ratio. This one's got a larger interference, reducing its ratio, and so on. And the only way to really get at that well is to do this ratio mixing experiment. But I wouldn't recommend doing 100-to-1 or 1,000-to-1 because that's just a little more challenging to get accurate quantitation on. Yes?
Is there not a tool to predict given a peptide that you have these auto interferences? Oh, there we go.
There is now.
Someone should do that.
So in this experiment, there was not a tool. And the only way to do it was to have Skyline generate potential product ions. And it was a very laborious process. And I sat with Brendan over the phone asking him to help me with this because I had to check everybody's data sets to make sure the different vendor platforms that were using different transitions and different product ions didn't have this problem. And so we had people run these experiments and I had to go through all the data with more wine. And so he enabled this thing called duplicate ions where if this is your spectral library and you have one, you click it, and when you click it, the ones that are duplicate ions that are going to potentially cause problems are shown. So you can go into your list and delete, or mark them. as potentially bad. Okay. All right, so optimizing collision energy. This is something, we've got 15 minutes, okay. Why do we optimize collision energy? People using triple quads, do you optimize collision energy for your stuff? How? Do you infuse it or do you do LC separation?
LC.
Okay, yeah, that's the new way. It's so much better. So one of the reasons that you can optimize collision energy is because shown here, each of the product ions, which is what comes out at the very end, out of Q3, is generated individually. So you monitor one at a time sequentially. And the triple quad, so it selects your precursor, fragments it, generates all the ions, but only one is detected at a given time. And so that means in here, in Q2, the collision cell, you have an elevated gas pressure so that the ions can go in and like bump into stuff. And then you apply a voltage, a collision energy voltage. And that voltage usually has a relationship with the mass to charge of the peptide. And so the bigger the mass to charge, the more energy you give it. And then it can also be optimized so that every product ion you generate gets its own. So it's possible to specifically improve signal on a transition to transition basis. Now, in the old days, people used to sit in front of their triple quad and infuse with a syringe pump their peptide. And then so you would get a stable signal, and then the collision energy voltage would be ramped on the instrument. And as it ramped, you would be generating more and more of a product ion, and then you would reach some maximum, and then it would go back down. So this is called a breakdown curve. And it's handy because this tells you this is the highest intensity you can get. It's at this collision energy value. That's what you want to use to generate big product ions for your peptide, for those products. And this can be done for every fragment that is made from a peptide. Now, because, so let me back up. Once you have done this for a number of peptides, you can plot the mass to charge of the precursor versus collision energy. And when you look at just the precursor value and what's optimal for that precursor, you can kind of like for retention time, you get this regression where you get a collision energy equals a slope times the mass to charge of the peptide plus some offset. And this one is not a good example because also it doesn't take into account like post-translational modifications and other things, but this just gives a reasonable example of what you can do, and there is a positive correlation. So this is an example of optimizing for collision energy in Skyline using a chromatographic setup. And that's a lot nicer because you're not sitting there infusing a peptide with a syringe, cleaning it out, having to do that again. It's very time consuming. And so if you have the LC introduce it, even though your peak is coming out on a chromatographic time scale, the instrument's so fast, it can change collision energy on the millisecond time scale. So if you go into Skyline under transition settings, and then you'll see this window, and you click, it shouldn't really matter, edit current, whatever the one that it's on, you should see something like this, and this is showing for each charge of your peptide, there's a slope and a y-intercept, and that's the regression plot that's set up for whatever instrument you just edited current. You can customize this for your instrument. Most models of the same instrument, for example, all 4,000 Q-traps and 5500s or Quantivas will have a regression equation that works on that model. And it'll be different from different models and different vendors. And this is empirically determined. And so you can always ask your vendor if you don't have a regression in there, but Brendan and his team do pretty well updating it. Right. And then here are the settings you would set if you wanted to do LC optimization of your collision energy. Step size is in volts, how much you would vary the volt step to generate that breakdown curve. And the step count is on either side of what this equation predicts. So the equation predicts the red bar. This is a response using the default collision energy from the regression equation. And here we go up by 2 volts, 2, 4, 6, 8, and down 2, 4, 6, 8. So we span a range of 16 volts. a collision energy, and then plot the data. And you can see based on this, 2 volts less than what is predicted is probably best for this peptide, but it's not off by that much. And I have Skyline files in here with data that we can walk through showing how to do this. But the step-by-step is to import collision energy optimization results. You normally have to run a method that Skyline sets up for you that will optimize the collision energy on the fly for your targets. When you generate those data files, you import them by going File, Import Results, add 1 new replicate, optimizing collision energy, and then you can select the series of data files, and what's imported into Skyline would look something like this. Now, the way that data are normally imported into Skyline, it has the transitions set to all, and this is what you would see, which just looks like all the Skyline data we've shown up till now. If you change the transitions to single, then it'll show you for that precursor, all the different colors now are different collision energy values. So the signal at each different collision voltage. Let's see. Before you do collision energy optimization, make sure you've got the right peptide picked, otherwise you get useless data. And you can see this is, when I import data into Skyline, this is what it looks like before I go through and manually make sure everything looks good. And so there's a little cleanup that sometimes needs to be done. And then after you do the collision energy optimization, if you click Use Results and Show Graph, Use Results will update those voltage values, the slope and y-intercepts. It'll update it with real data. And so what's shown here is the setting that's in the table that will predict collision energy. And now using used data that we just generated, these are the new slope and y-intercepts. And so they may look different, but if you put them in Excel and figure it out. So these are the collision energy values. So if I use the regression from before I optimized for these master charges, I get these 2 values. And then after I optimized and I use results, my collision energy regressions changed, but the actual calculated value isn't off by that much. So that's before and after, the same value. These 2 are a little bit more separated. Sorry, my animations are off. But it could be because I had some data throwing it off. Also, +3s are a little more challenging because we don't tend to have as many +3 precursors. And so it's hard to get enough data to get a good regression built. And so this is all stuff that's pretty straightforward to do in Skyline. The other thing about why the +3s may be a little more off here is because +3s have a tendency to generate +2 product ions. And if we use the precursor level optimization, any product ion that is doubly charged doesn't follow the regression very well. And so what this shows is the red is what was predicted by the 3+ precursor collision energy regression, but the optimum is actually up here. Now that's an intensity improvement that I would totally change my collision energy for, but it can't be predicted right now because it's based on the product ion mass to charge and charge, not the precursor. And so Brendan and I have spoken about this, and if I can get him enough data and we can model it, then there is a chance that we can get product ion level collision energy equations to work. And this happens on all triples. It's not just, it's a ion physics thing. It's not an instrument thing. So you can optimize at a precursor level. This would be great for like a Q-exactive or a Q-TOF where you're not generating product ions sequentially. You're doing them all at once and just one collision energy. But you can also look at the product ion level. So here's just an example. I selected a transition, the Y4, and it's showing the best collision energies for that. So what does it buy you? It doesn't always buy you much. I optimize if I have time. I optimize if I'm going to be gone for the weekend and I can just let the system chug. I'll put in the methods and run it. But oftentimes, this is working with the regression equation. That's the intensity we get, and after it's been optimized, like that's not even a 10% improvement. So And these are a bunch of different peptides, starting with the same collision energy regression and then optimizing them, you know, soup to nuts. It really, this was the only one where we got a significant twofold improvement in that particular peptide. And so it's not always necessary, and there is no consensus on should you do it or shouldn't you. And the last word is, don't forget about post-translational modification. So this is what I was talking about before. When the peptides fragment, in the collision cell, they usually fragment along the peptide backbone very predictably. If they have side chains, what can happen in CID is the energy that it experiences when you hit it with the voltage is that it rearranges and pops off the modification. And so softer methods or lower energy methods of dissociation, like electron capture dissociation and electron transfer dissociation, can preserve post-translational modifications, and they don't pop off quite as quick. So unfortunately, triple quads are not ideal at working with PTMs. So if it's something that is site-specific and you need to retain it, then it may not be the best instrument. Okay, so transition selection and optimization, they are important. The other thing you may find is when you're optimizing and you pick a peak that you think is your peptide, if it's not actually optimizing, it might not be the right peak. And so that's just another way where if you're optimizing and trying to improve the signal, you should hopefully see some kind of improvement. Otherwise, it might not be what you think it is. And balance the sensitivity gains you need. You don't have to optimize if you're looking at high-level targets in plasma samples where you've got an abundant supply. But if you have to get down to very low sensitivity levels and you would rather optimize to get a twofold improvement rather than do an enrichment step, which would be more sample handling, then it may be worth it. And always worry about interferences. The people are different, their daily intake and diet are different, so plasma is different. You don't know what can be interfering with your sample. You don't know what can be interfering with your peptides, and so it's always important to keep an eye out. And there's nothing wrong with manually looking at your data, but it's a balance. Just remember that there is software support most of the time, and if there isn't software support, you go and tell Brendan. And the secret here, and I know he's gonna hear this, is if he gets 3 requests for the same feature, it goes to the top of the list. Pair up, okay. All right, so that's, we are about at lunchtime. If there are any questions, I'm happy to answer them. If anyone wants to spend some time going over some of the files, I can show you how to do that too. Other than that,